Well, good afternoon, it's Charlie ZL2CTM. Hey, before I start, thank you very much everybody for the good ideas that have been rolling in. Got quite a big list now of ideas ranging from test equipment to radios to receivers and everything in between. So that's great. I'll put up in the show notes a bit of a shorter list, an immediate list, so to speak, of what I might look at. Not necessarily in a particular order, but certainly things that would be of use to me as well. Today, one thing that I don't have in the shack is a proper two-tone oscillator for testing single sideband transmitters. So that's the first thing I've decided to build. I have been using a cell phone app to date with pretty average results or performance. So anyway, you may recall as a lead-in, the transceiver over the back here for the antenna tuner, I had used an RC phase shift oscillator. While that works well, to be honest, it was a bit of a pain to actually get up and running, to get exactly the loop gain, just to give unity loop gain or just over to get it to start up, to get nice linearity. It took quite some time to get it to go. So what I've elected to do for this particular two-tone oscillator is to go with a Wein bridge, and I've elected to use some common, easily sourced op-amps, the LM358 in that particular case. I've sort of gone, this is nothing new here. This has been done before, but I've sort of just started from first principles and worked through. We'll look at the circuit in a sec, but I've tried to use buffer amps as well, just to minimise loading on the various stages. Anyway, so let's look at the circuit, and then we can come back and flash up the oscilloscope and have a look. Right, so the circuit itself is pretty straightforward. There's I guess, three main parts to it, or two main parts. There's the oscillators and then the summer. So we've got two oscillators here, dedicating an LM385 chip for each oscillator. The LM358 is an 8-pin device which has two op-amps in it. So the first op-amp, or notionally the A ones, is the oscillator, and then the B side is the buffer amp. The 700 Hz oscillator from a configuration point of view is exactly the same as the 1700 Hz, just the value of R and C is subtly different, which we'll look at in a sec. And that feeds into a summer amp, into its own buffer, and then out it goes. So starting on the left hand side, right, so the Wein bridge oscillator has in the feedback circuit a bridge which is made up of two resonant circuits, a series and a parallel. The values of the resistors and the capacitors are the same. So for the 700 Hz oscillator, these two values are the same, and then for the 1700 Hz oscillator, different values, but again the same. So R2 equals R2, C2 equals C2. They're feeding into the non-inverting input, and the overall gain of the circuit has been set by this resistor here and this resistor. So common verbiage for the op-amp would be RF for the feedback resistor, and then Rin. I've, as we'll see in the calculations down the bottom, I've just elected to make that a 10K trim pot, which allows me then to tune the overall gain of the stage to get that loop gain, or the closed loop gain spot on one, or unity gain. I should say too that at the frequency of oscillation, or 1 over 2 pi RC, which we'll look at in a sec, the voltage being presented at this point here is a third of V out. So there's a third of V out there. Then we need to have a gain of 3, so a third times 3 gives us our unity gain at this point. You'll see across that 10K ohm resistor, two back-to-back diodes. I'm using 4148s. That comes out of an application note for another type of op-amp. These are matched. Some of the documentation available talks about having matched diodes, and what these diodes are doing is basically doing gain compensation. So as the output tries to grow, these will conduct more and more, which will then cut the overall gain down to bring it back down to a stable level. So the 10K ohm resistor here sets a level, and then these two diodes here keep it at that level. Because with an oscillator, the output is being fed back to the non-inverting input, so the output's trying to grow and grow and grow and grow. So that's just a way of keeping that gain or the output stable at a point. Like I say, they're matched, and we'll see later on that I just used the same process that I used for the double balanced modulators in terms of matching those diodes. Another thing to point out, I'm using, or I don't have a split power supply. I've got a single ended power supply, so just VCC and earth. So therefore, with an op-amp, I need to provide a virtual earth at this point here for the two oscillators. So that virtual earth is coming from a voltage divider, just using two 10 k ohm resistors there to minimize the current coming off the 12 volt source. And that sets that point at 6 volts, so halfway between VCC and earth. So that's the virtual earth there, with 100 microfarad capacitor there, just to give that from an audio point of view, because these are both running at audio, a common earth as well. So as you see there, that's the common earth there, and also being fed down into this one. The summer, which we'll get to in a sec, also has its own virtual earth coming in through, again, two 10 k ohm pots. So what else to say about, so we talked about this, we'll look at the values for that in a sec. This oscillator down here is exactly the same, but just different values of R and C to come up with a different frequency. Going through buffer amps, nothing special there, that's the second half of the chip. So just going direct couple straight into the non-inverting input, and then the inverting input is tied directly to the output. Through a DC coupling capacitor, just using 100 nanofarads. I'm not after heaps and heaps of audio gain here, so I can get away with just using 100 nanofarads. Nice and easy and quite common. Two switches there, so you can elect to have, with the switch closed, a two-tone oscillator, or with one or the other switch open, well, one of the switches open, you can then have this running as a test oscillator at a fixed frequency, either the 700 odd or the 1700 hertz odd frequency. Right, for the summer itself, we'll see the maths in a sec. Just running with a variable resistor for the feedback resistor there, to allow the overall two-tone oscillator to have variable gain or a variable output. There's obviously different ways of skinning a cat there. That could have been dropped across an output pot there, and then the tap going into the buffer, but I've just elected to keep things simple and just have a variable resistor there, which has worked well, and then just arbitrarily set the input resistors to be 10 k ohms. So exactly the same setup for the buffer amps. All three buffer amps have the same characteristics, a very high input impedance and a very low output impedance. So in this particular case, I want the two-tone oscillator to be approximately 600 ohms, so that's in line with the dynamic microphones that I have for the transmitters. So I'm going to use, close enough, a 560 ohm resistor there to have an overall presentation of around 600 ohms. So getting down into the actual maths, so we talked about the frequency, the first frequency around 700 hertz and the second frequency around 1700. As mentioned before, our frequency of oscillation is 1 over 2 pi RC. And what I did at this point here is rather than just punching in values of R and C into a calculator to see what came out, I decided to use a simple spreadsheet, just using Google Docs or Google Sheets, I think it's called actually, or Numbers, whatever it is, to do all the hard work for me. So there's different ways of doing that. You could have had variable resistors with a set capacitor. In this particular case, I had a variable resistor with, say again, a set resistor with a variable capacitor. So those values there are in nanofarads, and then outputting what the frequency is. So sitting below these cells here is the formula which is running around and doing the 1 over 2 pi RC using these two values here. And yeah, right, so it turned out that, let me just scroll off a bit, that a 47 k ohm resistor and a 4.7 nanofarad capacitor comes out at pretty close to the 700 Hertz, or in this case 720 Hertz. I elected to just see what, if I was to use again 4.7 for the second oscillator, what value of resistor would give me in the region of 1700. And as it turns out, I'm using 1% capacitor, 1% resistors here, and I've got a 20k ohm resistor. So 20k ohms with 4.7, when you put that into the formula, 1 over 2 pi RC, you come out at 1693, which is pretty close to our 1700. Now you didn't have to use 4.7 nanofarads. You could have used any one of these other values, but then you'd have to go looking through to find out what resistor would be suitable to create that 1700. So this, I just punched the value in here. These all copied it and then flowed across. So like I say, a lot faster than feeding numbers into a calculator one by one to see what would come out. So let me just zoom back a bit. Right, so that's what we've got here. So for arbitrary, I just set C1 and C2 for both the two oscillators to be 4.7 nanofarads, and like we just saw, it came out with an R1 value of 47k and an R2 for 20k to give those two frequencies there. Not harmonically related. I should have said that before. I don't know if I did. One of the things you need to make sure with a two-tone oscillator is the two frequencies are not harmonically related. So 720 times 2 is not that. 720 times 3 is certainly not that. So I'm not related at all. Right. The other thing too, we mentioned before that we need to have a loop gain of just over 1 to meet our Barkhausen's criteria. So Barkhausen, if you recall, we need to have an input, the frequency, or not the frequency, sorry, the phase has to be multiples of 360 degrees with a loop gain of 1. So in this particular case, we mentioned that with a Wein bridge oscillator, that bridge itself presents to the non-inverting input a third of V out. So therefore I need to have a gain, an open loop gain of the amplifier itself to be just a bit greater than or equal to 3. So 3 times a third comes out as our closed loop gain of 1. So our being an inverting input, it's minus RF over Rin, and we mentioned before that I was looking to use 10 k ohm trim pots just to be able to individually set the amplitude of each of the oscillators. So a 10k pot gives us an Rin then for these two resistors there, sorry, of 3.3k. So that's about right. I mentioned before that those were matched 4148s. I must actually double check with my multimeter to see if the diode test mode would actually do this automatically, but I've done what I've done before, and I'll check the test mode later on. But in this particular case, it was a 12 volts through a 10 k ohm resistor to reduce the current to below the 300 milliamps, which is the maximum current allowed through a 4148. It actually turns out to be 1.2 milliamps, which is fine. And then to use a voltmeter to measure the voltage drop across that diode. So I got those as close as I possibly could. So we had values of down to, in fact, some cases it was down to tens of milliamps. Well, at least within 10 milliamps, I should say. Millivolts, am I saying? Millivolts. Right, right. For the summer itself, you can see there that the RF, or the feedback resistor for that one, I'm just notionally using a 50 k ohm pot to be able to adjust the feedback, and then so therefore I'm just setting those to 10k. So 50 divided by 10 gives us a gain of 5, which will be fine. We talked about the virtual earth before, so no need to mention that one again. The other thing which I will just chat about, and I'll demonstrate it in a sec, I quite often run, like the antenna analyzer for example, because it's an Arduino based device, I run a lot of things at 5 volts. So I wanted to see how well, this is designed for 12 volts, but I was looking to see if it would perform at 5 volts, and it does. But you will see that when you run it at 5 volts, you need to crank down the gain of the summer because you're just saturating. There's not enough VCC or not enough voltage swing before you start bottoming out. So that's the particular. No, in that particular case, you need to change the feedback resistor, which is the variable resistor here, from a 50k to 10k. And as you'll see in practice, with 12 volts with a 50k pot, getting a good 8 volts peak to peak, and then with a 5 volts we're getting 1.75, which still I'm pretty sure will be way more than enough to feed into an SSB microphone socket to drive that. But either way, okay, so let's just have a look at the test setup. So at the moment there's 2 pots just sitting here. There's the 10k ohm pot and the 50k ohm pot. Just scoping the output of that 560 ohm resistor. And I've got the probe on 10 times just to minimize the load on that. I mentioned before, that's the 3 oscillators, so oscillator 1, oscillator 2 and the summer. Each one has, for the second op amp, is the buffer, which is that yellow wire there going from the output to the input of the buffer. And the 2 trim pots, two 10k trim pots to set the gain, and then those matched back-to-back diodes providing the gain compensation. Right, so at the moment the output is running on, if I was just to crank the now up to 12 volts. So we've got 12 volts there. We can just zoom up a little bit. And we are running on the, let me just swap back to the 50k pot. So you can see there that pot gives us some nice variation in gain, so we can have the overall 2-tone oscillator giving us a variable output. If I was to disconnect the output of each oscillator to the summer, we can see now we're locked on the it's the high frequency one, and if I was now just to connect that back up and disconnect the other one, that's the 700 Hertz, or in this particular case 720 Hertz. So that's effectively what would happen if we were to open up those 2 switches. Of course, you open up both switches, you'll get nothing out, but that goes without saying. So anyway, so back to both oscillators now feeding the summer, and then the summer's feeding the output. We mentioned before that if this is now on maximum output, if we now were to reduce our voltage down to 5 volts, we can get see there's some horrible, we're going from rail to rail. We don't have enough voltage to do what the gain is being asked to do. Now I could reduce, which I'm doing now, that 50k pot on the summer, so I could actually work on that, but it's very easy just to sort of go a little bit too far, and if you don't have a scope, then we're now introducing a whole lot of distortion because we're no longer a nice sine wave. So if I was just now to swap over to the other potentiometer, so this is now a 10k ohm resistor, we can see there that we have a lot less output to play with, but we get nice now from maximum down to minimum, so we don't get any of that kind of clipping. So I guess it's up to the builder. In this particular case, I'm still sort of erring on if I'm going to run this off 5 volts or 12 volts. I might start with 5 volts so that I can use, have a similar setup to what I've got for some of the other test equipment, and we'll just see if that's going to be sufficient drive for the transmitter. If it's not, then I'll just revert to 12 and insert that 50k pot and go from there. Okay, I think that pretty well summarizes everything I wanted to talk about. So I talked about virtual earths, talked about the buffer amps, now the buffer amps are there, of course, like any other buffer amp, to minimize any variations down here from affecting the oscillators. So and the fact that they're sort of like freebies, so to speak, because they're already in the op amp. And I was going to dedicate one op amp per, or one LM358 per oscillator to keep them sort of separated. It was easy enough just to use the buffers. So, right, I think I'm starting to ramble now, so I will say 73s for this one. I'll now go and solder this up, make sure it's working, and then probably look to feed that into the SSB rig and see how that performs. Okay, 73's all I should say. I hope the theory was correct there. And happy soldering. Okay, 73's all.